Okay, today we're going to pick up on our Lewis structures and continue that stream of thought by looking at something else here. Suppose we just looked at something like the chloride ion, Cl-. What kind of Lewis structure or dot symbol would this have? Well, chlorine, remember, is in group 7. So we have 7 valence electrons. 1, 2, 3, 4, 5, 6, and 7. But remember, now we have a negative charge. And the negative charge means I have to add an electron. So this would have a total of 8. And I would add it here to the single to pair that up. And so this would be the Lewis dot symbol for Cl-. Okay? So anytime you see a negative charge, tell yourself I have to add one to that particular atom. Okay? And so we say that chlorine has a formal charge of -1. Okay? So here we're introducing the concept of a formal charge. Okay? Let's look at another example. Let's, for example, look at CH3+. Okay? So here, let's draw our atoms out. Let's put our valence electrons. Hydrogen has 1 each. Carbon has 4. And now we will pair up the singles. So I can have 3 bonds to the carbon. But now I have this leftover single. What am I going to do with it? Well, that's where the positive charge helps us. It tells us what? I get to remove a valence electron. And so this will be the one that we end up removing. So if we draw the Lewis structure, we would get this here with carbon having a formal charge of +1. Okay? Okay, so this concept of formal charge is very, very important. Okay. Here we notice some carbon likes to have what? 4 bonds on it. If I take away a bond, okay, it gains a positive charge by doing so. Okay, let's look at some more of these. Let's look at H3O+. Okay, remember this is called the hydronium ion. That we will be using a lot in organic chemistry. what is the Lewis structure for this? There are my atoms. Now let's write the valence electrons. Okay, so there's the valence electrons on the atoms. Okay, you note I'm waiting till the end to use my charge to my advantage. Okay, so don't try to do it ahead of time or you could get a little bit messed up. So now let's play connect the dots. So the hydrogen and oxygens can connect. But now I have a problem. I don't have any more singles. Well, this is where now my positive charge can help out, can it? Because now it says I can remove one of the valence electrons. So let's go ahead and remove this one here, and that allows these two to combine. And so we get a Lewis structure like that, where the oxygen has a formal charge of +1. Okay. Why? Because I removed one of its valence electrons in order to get that structure. Okay? So the hydronium ion ends up just having one lone pair on the oxygen. Here we see another important concept. Oxygen will be neutral if it only has 2 bonds. But if I gain a bond on oxygen, it becomes positively charged. Okay? We'll see later on if you lose a bond, it becomes negatively charged. Okay? Well, let's work backwards at this point. Okay? Let's suppose that we worked backwards. Okay? And let's suppose I gave you that Lewis structure. Okay? And you didn't know ahead of time if there's a charge in there or not. Okay? And I asked you, what is the formal charge on that oxygen? Can we figure it out if we go backwards? Yes. Let me give you the rule by which we do that. The rule is we look at the atom in question. Here it's oxygen, and we ask what group it is. Oxygen is in group 6. Okay? Next, what we do is we subtract the valence electrons that are shown in the molecule on oxygen. Okay? So here's where you're going to follow me. Something new for you. So let me count them. 1, 2, the lone pair. Then for each bond, I'm going to count 1. So I get 1, 2, 3, 4, 5. So there's only 5 valence electrons here. So I subtract, and I end up getting +1. Okay? So in other words, my valence electrons, which it likes to have 6, I'm 1 short, so therefore my formal charge on oxygen is +1. Okay? We could have done the same thing over here to the CH3. let's suppose on CH3, I did not know what the charge is on carbon. Let's figure it out. Carbon is in group 4. Now I want to subtract the valence electrons. Where are they? 1 for each bond, so 1, 2, and 3. So 4 minus 3 is plus 1. So the carbon had a formal charge of plus 1. Okay? Again, this concept of formal charge, very important. Let's do some more examples. Let's look at this one here. Here we have nitrogen with 2 hydrogens. And I want to get the formal charge on the nitrogen. Nitrogen is in group 5. Okay. Now, what are the valence electrons that I'm going to subtract? Okay, so let's count them. 2, 4, then 1 for each bond, 5, and 6. So if I subtract 6 from 5, I get a -1. So here, nitrogen would have a formal charge of -1. Okay, that's why if you ever see NH2, it'll always be included as with a negative charge with it. Okay, let's do one of the more famous ions, the OH. Okay. So again, oxygen is in group 6. And what are the valence electrons? 2, 4, 6, and 7. So that gets a negative charge. And as you know, OH always comes as OH minus. Okay, the hydroxy ion. Okay. So this formal charge is very important as we're going to be using it throughout the course, and so we'll be expecting you to be able to draw molecules that have a charge in there, if indeed they do. Okay? So make sure you have this formula of formal charge mastered. Okay, in this chapter, there is a section on resonance theory. What we're going to do is skip resonance theory, that's section 9, and we're going to hold that way off into organic part 2 to cover that, okay? Because we really don't use it in this course, so we're going to hold it off to 242 so that where we do heavily use it, we can use it there. Okay, let's look at some other topics in this chapter. Okay, let's look at electronegativity and dipoles. Okay, another important topic. If we were to draw a picture of the periodic table, remember that the most electronegative atom was fluorine. Okay? And so as we move in this direction up to fluorine, our En, or our electronegativity, increases. Okay? So anything close to fluorine, very electronegative, things like oxygen and chlorine, nitrogen. Okay? But fluorine is the most electronegative atom. What does it mean if an atom is very electronegative? Okay? Electronegativity refers to the pulling power of an atom in a molecule on bonding electrons. The pulling power, basically, on bonding electrons. Okay? So if I had this stick here in my hand, and I were to let you grab the other side of the stick, and suppose you were stronger than me, your electronegativity would be greater than mine, because you can pull stronger than I can. That's the same thing for these atoms. Fluorine is the strongest puller, and then everything else gets a little bit weaker as you go away from it. So let's take a look at some examples of how this works. Let's look, for example, at a bond between carbon and fluorine. We've already learned that fluorine is the most electronegative atom. And so what we can do to symbolize that is draw this arrow like this over top of it. And that arrow is what's called the dipole moment. Okay? So make a note of it. We always point our dipole moment toward the most electronegative atom in that bond. Okay? So as a result of that, what happens? Well, these bonding electrons end up what? A little bit closer to the fluorine. And remember that electrons are negatively charged, so the fluorine's going to feel that extra electron and start building up a negative charge. And so we draw this symbol, which is the delta symbol, which stands for a partial negative charge. Okay? It's not a full charge. Okay? It's not a formal charge. It's a partial charge, showing that there's some negative characteristics to it. Since the carbon is losing that electron a little bit in that bond, it gains what? A partial positive charge. Okay? So if in the bond there's a partial negative charge, there will always be on the other side a partial positive charge. As a result of this, we say that the bond is polar. Okay? The bond is polar. What does it mean if anything is polar? It means what? Something at one end is different than that at the other end. If in this classroom, for example, we wanted to create a polarized classroom, we would maybe put the girls all the way over here and the guys all the way over there. Then the classroom would be polarized. Here it's polarized not by male-female, but it's polarized by positive-negative. Okay? If we didn't have partial charges, then the bond would be nonpolar. What would be an example of that? An example of that is if you had two atoms that were the same bonded together, don't you? Okay? So both are of equal electronegativity. So here we say that the bond is nonpolar. And so there would be no partial charges on either atom. Okay? Let's look at another molecule. Let's look at something like this here. Sometimes a molecule can have more than one dipole moment. Okay? Here, chlorine is more electronegative than carbon. So we have a dipole moment there. And we have a dipole moment there. So we would have two dipole moments. One of the reasons I drew this molecule is to show that there's never a dipole between carbon and hydrogen. That ends up being another nonpolar bond. Okay? So if on an exam I ask you to draw the partial positive and negative charges on a molecule, never put them on between carbon and hydrogen. For this one here, you would show it like this, the two chlorines, delta minus, and the carbon being delta plus. Okay? So that is a review of electronegativity that you should have had in general chemistry. Make sure that you can draw dipole moments on bonds and partial charges on the different atoms. These will be very crucial when we get into chemical reactions of molecules that we'll see later on in things like chapter 6 and chapter 7. Okay? Okay, well, let's look at another topic in chapter 1. And in this topic here, we want to look at the topic of drawing structures. Drawing structures. Okay? Let's start off by looking at this molecule. In this molecule, we've drawn the Lewis structure, haven't we? Where we've shown all the bonds between carbon and hydrogen. So that would be the Lewis structure. Well, we could end up condensing this a little bit. By doing this here. This is what we typically do. We typically condense the carbon-hydrogen bonds and shrink wrap them. So there's 3 hydrogens on that carbon, so CH3, and 3 hydrogens on this carbon, so that's a CH3. And then we oftentimes just leave the bond between the 2 carbons being shown, okay? So this bond is between carbon and carbon, okay? Even though it looks like it's carbon to a hydrogen. No, that carbon is bonded to that carbon there, okay? So make a note of this designation because we're going to be using this a lot, okay? So for example, if I drew this condensed structure, you should know what is going on here, that these 3 hydrogens are bonded to this carbon, these 2 hydrogens to this carbon, and these 3 hydrogens to this carbon, okay? And these bonds shown are between carbon and carbon, okay? So that's the first way we can condense structures. Another thing we can do is write what's called the molecular formula, okay? Remember what that is? It's simply giving you the recipe of the molecule. So this one has 2 carbons and 6 hydrogens in its recipe. The molecular formula doesn't tell you anything about the structure, okay? All it's concerned about is how many pieces are in that structure. So if we were to write the molecular formula for this, what would we have? 3 carbons and what? 8 hydrogens. So that would be C3H8. Make a note of it too, that we always put carbon first and then hydrogen, okay? Let's look at another structure. Let's suppose we had something like that. You should realize what is attached to what. Okay, so these 3 hydrogens would be on this carbon. This carbon would be bonded to that oxygen. That oxygen is also bonded to this carbon. And this carbon has 3 hydrogens on it. And so if we were to write out its molecular formula, we would write C2, H6, and then O. Okay. Note that I put the oxygen after the hydrogens. Okay? So always carbon, hydrogen, and then after this point, everything goes in alphabetical order. There just turns out to be one kind of atom at this point, an oxygen, so we put it there. But suppose we had this kind of structure. see these structures can start to get more complicated. Okay? But here we have the carbon with a chlorine on it this time and 2 hydrogens. Then that carbon's bonded to this oxygen. This oxygen's bonded to that carbon, which has 2 hydrogens on it. Then that carbon's bonded to this carbon. Doesn't have any hydrogens. It just has fluorine, fluorine, carbon, and that carbon. And then this carbon has 3 hydrogens and back to that carbon. Okay? So what if we had this structure and we wanted to write the molecular formula of it? Well, the carbons go first, so we have 4 carbons. Then the hydrogens, we have what? 2, 4, and 7. And then everything else. But I put it in alphabetical order. So chlorine, one of those. Then I got 2 fluorines. So I show those. And then I have the 1 oxygen like that. Okay? So that would be the molecular formula for this molecule. Okay? Note that you could rearrange atoms and get a different molecule with this same molecular formula. Those are called isomers, or structural isomers, which we'll get into later. Okay? But you might want to make a note of it at this point, that just because I have a molecular formula, it just doesn't mean that there's only one possible molecule with it, but there could be more than one. There could be 2 or 3 or 4 or more, okay? And those things are called structural formulas, giving us more than one, which are called isomers, okay? So we'll deal with isomers a little bit down the road. Okay? Well, as we start to wind up in here, let me introduce you to something else. Let's suppose we had this molecule. Okay, note this molecule has 5 carbons and 12 hydrogens. In organic chemistry, we're going to be dealing with another way of drawing these kinds of structures that's going to be new to you, but it makes it very easy to draw and much more easier to see with the eye. Another way to redraw this molecule is like this here, with these lines running together. Okay? So this is what's called the line bond structure. Okay? So this thing down here is the same thing as what's up here. How's that? Okay? So make sure you follow me here. At the end of each line, or at a peak or a valley, those represent carbon atoms. Okay? So I have a carbon, 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 carbon. Okay? So those are my 5 carbon atoms. Okay? You might say then, well, okay, I can see the 5 carbon atoms, but where are the hydrogens? The hydrogens are understood. Okay? In a sense, I don't really care about the hydrogens. I just kind of put them in my back pocket, but they're understood. You say, what do you mean? Well, remember this very important rule. Neutral carbon always has 4 bonds attached to it, okay? So let's take a look here. This carbon, I see 1 bond to another carbon, right? So how many would be left over? 3. And those 3 are these 3 hydrogens, okay? So whatever bond I don't see there, I'm assuming the other bonds are hydrogens. Just like here, this carbon is bonded to what? 2 carbons. So I have 2 left over. So I have 2 hydrogens on that one. Same thing here, a CH2, a CH2, and a CH3. So you can always say that a line, the end of a line is always a CH3, right? And at this point, a peak or a valley is a CH2, okay? So this is the kind of drawing we want to start getting used to. It's new to you now, but as you pick it up, you'll delight in drawing molecules this way, okay? So let's go ahead and end class here, and we'll pick up on drawing more of these kinds of structures next time.